Hello Mindsetters, welcome to today's grade 11 physical sciences show. Today we have a special revision lesson on light. We have selected highlights from lessons shown earlier in the year to help you with your revision. Please send us your questions and comments on Facebook on facebook.com/LearnExtra or on Twitter @LearnExtra so we can help you revise. Don't forget to download today's show notes on learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with the revision.
Right, let's go through some of these questions. Explain what happens to light when it falls on a mirror. Well, we've done it already. Light is reflected. And it will always obey the law of reflection. It's not going to go anywhere else. From a mirror, it's going to be reflected. From a black cloth, what's going to happen? It's absorbed. Now, window glass. Now, here, window glass is usually transparent. But even if there's little cracks on the window glass, what we find is it can do two things. It can mainly be refracted. So it will undergo refraction. It will be refracted. But it could get some reflection. And if there was some dirt on it, then we would say it could even be scattered. And that means it's spread out. It's like hitting the skittles and going in all different directions, okay? So hitting a little bit of dirt, bouncing off, and that's why we sometimes, if you get at a particular angle or there's a little crack on the glass, you can see different things happening. And those are the effects that we want to talk about. Now, have a look at the next question. First question done, next one is up. A beam of light moves through air into glycerine. Do you know what glycerine is? Abram?
Yes.
What do we use glycerine for?
Normally we put it on a lotion.
Yeah, you can find it. Ladies use it for their nails. And it's a colorless, clear, transparent liquid that's very thick. Eh? You pour it, and it's even thicker than syrup, but it has a fairly high refractive index. That's what we're going to have to calculate. So it tells us that the speed of light in the solution is found to be 2,04 times 10 to the 8 meters per second, and asks us to calculate the refractive index of glycerine. That's what we have to do. So, guys, what are we going to do? We know the formula. We told you. N equals C over V. Always write down the formula. There's a mark for it. Now, what are we given? We are asked to find the refractive index. So it really means that we've just got to do some substitution. First thing is, what is the value of C? Well, we know that. We can look it up, or we can remember it's 3 times 10 to the 8. And we can write down the speed of light in glycerine is 2,04 times 10 to the 8 meters per second. Now, you'll notice that the big number, 3 times 10 to the 8, is always the numerator, because it's always going to be bigger than 1. Okay, so let's have a look at what the calculator does for us as we plug these values in. We're going to say 3 exponent 8 divided by 2,04 exponent 8. We get an answer. And it gives us as 25 over 17. I want the decimal one, so I write SD from standard to decimal, fraction-wise, converting, and it gives me 1,47 to 2 decimal places. I'm going to write 1,47. Okay? So there you've got it. No panic. We just recognize this as a ratio that tells us that the speed of light in glycerine is less than the speed of light in air. Remember, speed of light in air is 3 times 10 to the 8 meters per second. It's slightly less than in a vacuum, but we're going to take it for our calculations as 3 times 10 to the 8 meters per second. Right, we're ready for question number 3. Now,
On that question, John,
yeah.
do some people drink glycerin?
Um,
Is it
n-
safe to drink?
No, I wouldn't drink it, you know.
Because they say it's good for sore throat.
You know what? I don't believe that. Lemon and honey, much better.
Because they say it has got sugar. Dr. James says so.
You know what? I think Dr. James needs to go and do some revision. It's not that good, I don't think. Okay, let's move on. So, question number 3. Question number 3 is a typical exam type question, one that doesn't involve too many calculations, but it will explain to us and illustrate for us this whole idea of refraction. You need to know these diagrams. You need to be able to draw them accurately with a protractor and a ruler. And there's some lovely practical investigations you can do as well. Unfortunately, we haven't got time for those today. So it says to us, draw a ray diagram to illustrate how light is refracted when passing through a rectangular glass block with a refractive index of 1,49. If the angle of incidence is 0, now guys, very, very important. Where is the angle of incidence measured from? Between the normal and the incident ray. So if it's 0, then we're going to put in the ray as follows. And I'm going to use some straight lines. And hopefully I've got a nice one. I'm going to take my pen and I'm going to put it right down there, and I'm going to draw it straight down. Now, the reason I've done that, I just want to move it so that it must sit right on top of the normal, because the angle of incidence is 0. Please take note, the angle of incidence is 0 degrees. That means the angle of refraction is 0, 2. And the angle of incidence at this surface is also 0. The angle of refraction is also 0. Now, has the speed of light changed? Yes, it has. It was traveling at 3 times 10 to the 8 meters over there. It was traveling 1,49 times slower in the glass block. This is glass. So it changed its speed. It slowed down. And here it speeded up again because it went from air to glass to air. So the point I'm trying to illustrate here is you need to make very sure you understand. Refraction is never defined as the bending of light. Okay? Bending of light occurs as a consequence of refraction. Refraction is defined as the change of speed of light when it enters another medium. Please make sure of that. Even some textbooks get that wrong. So make sure you've got that definition sorted. Now, the next part tells us that we've got this angle of incidence is 34 degrees. Now, guys, if we're going to do this one properly, then we need to go back and just quickly make sure we've understood Snell's law. And I want to just point out Snell's law to you because we had it a little bit further back, and I want to remind you of it, where we said Snell's law says this, that the refractive index of the first substance times the sine of the angle, the incident angle, is equal to the refractive index of the second times the sine of the angle of refraction. So please make sure that you get the first refractive index with the incident ray, with the angle of incidence, and the second with the refraction. And I just wanted you to make sure that you've got that very clear. So let's go back to our question. And we're going to, even though they haven't asked for us, I want to do it accurately. So I want to put down Snell's law here. And I'm going to say Snell's law says N1 times sine theta I is equal to N2 sine theta R. Now, what are we given in this example? We're told that it's moving from air, and we know the refractive index of air is 1, 0. We are told, secondly, that the refractive index of this glass block is 1,49. So N2, the glass, has a refractive index, N2, of 1,49. And the third piece of information we're given is the angle of incidence is 34 degrees. So I'm going to use Snell's law. I'm going to say N1 is 1. I'm going to substitute it in 1, 0. The sine, what was the angle? 34 degrees. That's the angle of incidence. Is equal to N2, 1,49. Let me just make sure that's correct. I did write it down there. 1,49, correct, is equal to sine of the angle of refraction. So once I've substituted in, now I can work out what the angle is. And I want to work out so I can draw the angle into my diagram and label it properly. So let's do that. And let's make sure that we've got it correct. So let's get up the calculator, clear that, and we're going to say, first of all, we're going to take the sine of 34 degrees. And then we're going to divide by 1,49. We're going to divide it by 1,49, and we're going to say that is equal to the sine of the angle of refraction. So what I now need is to take the inverse of that to get me the angle. So I'm going to go second function, or shift sine of my answer, and hopefully it will give me the right answer and tell me that the angle that I want is 22,04 degrees. I'm going to round that off and say, therefore, we can say angle of refraction is 22, and if I just rounded it off, it was 22,04. I'm going to keep it as 22 degrees. Okay, just to be quite simple. Okay, so now I know that what the angle of refraction is. So let's go back to my drawing, because I want to draw this accurately. Now, for you, if you were doing it accurately in a test or exam, you would need to use a protractor. I'm going to show you what it would look like, but I'm not going to be able to get an accurate measurement over here. It might just get too small. So the angle of incidence has to be 34 degrees. I'm going to approximate it like that and label it that this is the angle of incidence, and I'm going to say this is angle of incidence of 34 degrees. Now, what do we know? We know that this angle this light cannot carry on going there. It has to get smaller. In other words, we've already worked out what that angle is. It can't go straight on. It gets smaller. It gets towards the normal. So we used to just simply learn this, but now we can calculate it. And we can say, hey guys, it's not just simply a learning thing. We can actually calculate that change. We can say this angle now is the angle of refraction, and the angle of refraction is 20. What did we say it was? 22 degrees. 22 degrees. Now, very, very good that you can measure that and you can do it accurately. Make sure you draw your diagram big enough so you can get it all in. It's still quite small. What's going to happen at this point here? And I'm just going to change the color so that we can do it. What's going to happen at this second interface? Well, I hope you can see something here. From your geometry, we've got a parallelogram or a rectangle, which is a parallelogram. So you should recognize that the normal is a set of parallel lines, and the sides of the rectangle are also parallel. This means that I can say that the second angle of incidence is also equal to the angle of refraction. So if that's 22 degrees, then I know that that's the second one when we're moving from glass to air. Guys, I'm going to leave you to calculate the size of the angle, but I'm going to tell you what it is. Guess what it is? Can you guess? I guess that the angle of refraction here, the second angle of refraction, is going to be the same as the angle of incidence, which was 34 degrees. Now, you can go and confirm that, put it into Snell's law, do the calculation, and you will see it is. The important thing here is that you understand that this angle now gets bigger. In fact, I must do it like this. It gets a little bit bigger. My approximation sketch wasn't too bad, because what you should notice is that because these lines are parallel, this incident ray and this emergent ray are also parallel. So what happens? It bends towards the normal, and then it bends away from the normal, where that is R2, and that's I2. That's the parallel block. Now, guys, there's so much more that we can do, and I hope you can see how to do it. I want to go through one more example. I'm not going to do Snell's law on it, but I'm going to show you the diagrams very quickly. You must learn this. So it tells us that we must draw a ray diagram to illustrate how light passes through a triangular prism, glass prism, and it gives us the refractive index. It says the angle of incidence is 40 degrees. Again, you should do the calculations to do it. I'm just sketching it to help you get through it. Okay, I'm not even going to use straight lines. I'm going to do it freehand. I'm going to say the angle of incidence is that one, and that first angle of incidence is 40 degrees. It's going to bend. It's moving into a glass block. It's not going to carry on in that line. It's not going to carry on in that straight line over there. Let's put the pink one in so we can see it, because we need it. It's not going to carry on in that line. That's where it's not going to go. It's going to bend towards the normal. And I'm going to choose this one or this one, just change the color, and let's do it from there. It's going to get smaller. So let's make sure that we've got it like that. It's then going to strike this point, and guess what? There's a normal written over there. So there's the normal, and we're going to now recognize it's moving from glass to air, so it's going to speed up. It's going to bend away from the normal. In other words, it's not going to carry on going straight. It's not going to go straight. It's going to bend towards the normal, away from the normal at least. The angle's going to get bigger. So here the angle got smaller. This angle got smaller. This angle got smaller, first of all. And secondly, this angle got bigger. I hope you follow that. Now, look what's happened to the light. It was starting over here. It's gone to there. This angle between where it was starting and where it ended up, this is called the angle of deviation.
It's time for a break, so go get some water and grab a snack, and we'll be here when you get back. Welcome back from the break. Remember, if you need to revise any other topics, you can get the notes and watch all the videos from the Learn Extra live shows on learn.mindset.co.za. Or you can subscribe to our YouTube channel, youtube.com/mindsetlearn. You'll find that we've organized all the videos into shelves and playlists to make it easy for you to get what you want. Now it's time to get back to the revision.
So, here we go. We've got the following question. Question number 1. And just before I do question number 1, I want to remind you something. Guys, please download the notes and work through them. Even after the show, if you didn't have them before the show, download the notes. Practice, practice, practice. Okay, here we go. It tells us the following things. It says to us, you've got a rectangular glass prism that has a critical angle of 42 degrees. It says, draw a sketch to show what happens when light moves inside the glass towards the air and strikes the boundary. So there are 3 scenarios that we want to go through very, very carefully. Okay? And I'm going to take it slowly, and I want you to tell me if I'm getting it right. You think about it as we go. So I'm going to select a little rectangular block. I want it to have that and look like this. So have a look here. We're going to allow this rectangular block now to strike the inside of the prism. We're going to strike it first of all with the angle of incidence of what value? 35 degrees. Now we know that the angle, the critical angle was 42 degrees. So I'm going to sketch. I'm not going to measure accurately, but I'm going to sketch, and I'm going to say to myself, let's take the green line and let's put it over there. And we're going to say, use the green line as my angle of incidence, my ray of my incident ray. And it's striking that point, hopefully there. The angle here, angle of incidence is 30. How much do we want? About 35 degrees. What we notice, the angle of incidence is less than the critical angle. It's less than the critical angle. So what's going to happen? If it's less than the critical angle, remember this is glass and this is air. So what's going to happen? The light is going to speed up when moving from glass to air, and if it speeds up, it bends away from the normal. So the light is going to travel in this direction, and it's going to bend away from the normal. Okay? Notice that the angle of incidence is small, the angle of refraction is large. Okay, that's the first diagram. You got it? Situation is glass to air less than the critical angle. So what's going to happen if we change it now? And we're going to say, let's take this whole thing and let's just redo it. We're going to take this whole thing and we're going to do the diagram underneath of what it would look like for part B. Doesn't matter how fat or wide the object is, it's just that we want to be able to see it clearly. So we're going to say to ourselves, there's the normal. Now the angle of incidence is exactly 42 degrees. What do we know about 42 degrees for this particular type of glass? Well, 42 degrees was given as the critical angle. So what do we know? We have got the critical angle. And what does critical angle mean? It means at the critical angle, the angle of refraction is 90 degrees. That means the light is going to come out, but it's going to be bent along the surface. So it's going to go like that. Okay? No, not like that. That's too much. Let's just undo that for a minute. Let's do it again. It's got to go along that surface, and it's got to stay on the surface at an angle of 90 degrees that we'll indicate over here. So this angle is 90 degrees. That angle there was 42 degrees, and 42 degrees is equal to the critical angle. Please don't abbreviate. I'm allowed to abbreviate, but in your exam, please don't abbreviate, okay? I'll get a license from Ashraf who does the accounting to abbreviate. So I understand that's what's happening. So guys, what's the third scenario? What's the third situation? When the angle of incidence is 60 degrees. Now please remember, the angle of incidence is always measured from the normal. So let's do it again. Third scenario, we're going to take our third scenario, we're going to do that, and we're going to say, here's our normal, and we're going to measure 60 degrees from this position, and we're going to put in the critical, the ray, incident ray. Notice it's bigger. That's about 60 degrees. I'm just guessing here. We're going to call this the pink one. That's 60. Now, notice that the angle of incidence now is greater than the critical angle. If it's greater than the critical angle, what happens? Total internal reflection. Okay? Total internal reflection. Okay. You've got to get this right. It's not going to refract now. It's going to reflect in on itself. What's the law of reflection? The law of reflection tells us the angle of incidence, the angle is equal to the angle of reflection. So the angle of reflection is going to be inside, and it's going to look something like that. And notice here that this angle now, this angle is known as an angle of reflection, and it's 60 degrees as well. Okay, we need to be very clear that this isn't refraction. This is reflection. The light has changed its path. It was going in that direction, and it was coming out of that direction. So that's what I was meaning when I was using this little tray of water. When I shot the laser light straight across, it came out. When I did it from the side, then it was at a big enough angle, so it didn't come out here, but it came out the side. So it bounced around on the inside, and that is total internal reflection. Isn't that fascinating? Abram?
Very.
Okay, I hope you've got it, because if you've got it, then the other learners out there will have it too. So let's see if we can do one last question. I've got a couple more drawings to look at. What it tells me is to draw diagrams to show how you can use prisms to turn light through 90 degrees and 180 degrees. Right. Now, if we're using a glass prism, then we know that for glass, different substances are going to have different critical angle. For glass, we're going to take it to 42 degrees. Okay? The critical angle, 42 degrees is the critical angle. Perspex is quite similar, and we're going to have a look. So if we want to turn light through 90 degrees, this is how we're going to do it. We're going to take this triangle that is a 90, 45, 45 degree triangle. So an isosceles triangle where, stay with me, don't go to sleep just because I've mentioned angles and triangles and geometry. It's important. That length of side is equal to that length of side. Oh, that's a terrible 45. So let me just write it again. We're going to say that angle is 45 degrees. And this one is 90. And this one is 5 degrees too. So if you've got that in your head, then watch and see now what happens, how we can turn light through 90 degrees. We're going to take a beam of light, and we're going to say, let's make it hit this side with an angle of incidence of 0. So in other words, along the normal. The angle of incidence at this point, I, is 0 degrees. It's going to go straight through. Does that mean refraction doesn't take place? No, refraction does take place. The speed of light changes as it enters the new medium. But now, guys, look what's happening over here at this point. At this point, if I conduct a 90 degree angle, and I'm just sketching it, then what I hope you can see is that because this line is parallel to the bottom one, that this angle is also going to be 45. So this angle here, that angle is 45, that angle is 45. It tells me if I've got an angle of incidence of 45 degrees there, then is that bigger or smaller than the critical angle? No, yes, it's bigger. It's much bigger. It's 3 degrees bigger. So that means that the light is going to turn and it's going to come out over here. When it strikes this barrier, it's going to hit it at an angle of 0. Angle of incidence equals 0. So my light has gone through a whole change in direction. Remember when we talked about angle of deviation last time, we said what was the initial angle? What's the final angle? What's the difference between them? If I took my initial angle, and I'll just finish off here, that was my initial direction. That's my initial direction. And if I measure the difference between my initial direction and my final direction, that's 90 degrees. Last little point, which is point B of this diagram, is if I take another diagram, another prism, and I allow light to travel in this direction, I can get it to change through 180 degrees. I want you to go and see what the angles would need to be for that to happen. Okay.
Okay guys, I hope you are enjoying this revision session. If you are struggling and need help, please post on the page or submit your questions to the Learn Extra help desk. Now it's time to take a quick break, so don't go away. We'll be right back. Welcome back from the break. Remember, if you have any questions, you can submit them to the Learn Extra help desk. You'll find the details pinned to the top of the page. Right now, let's do some more revision.
We're told the following thing. A beam of light, a ray of light, is shone through a ruby. A ruby is a particular type of stone, and what we're asked to do is to calculate the speed of light through the ruby. Now, just let's go back to our table quickly. Remember I said we were going to refer to it. And there's our ruby, 1,76. Normally we'd have to go and find that. It would begin in the question, but I thought it was good for you just to refer back to the table. So how are we going to do that? We know that it's n is equal to 1,76. We want to find the speed of light. What do we know? Can we use Snell's law? No, we can't. We don't know two media. So what is the other equation? N is equal to C over V. Okay, we know C because we know that C is a constant, 3 times 10 to the 8 meters per second. Okay, we know that. So what don't we know? We don't know V. So whenever they're asking you for speed of light, you need to know it's this equation that we need to look for. So let's substitute, and notice I'm going to put 1,76 on that side. I'm now going to say my substitution 3 times 10 to the 8 goes over there, and I want V. Guys, I can do this. I can do these type of calculations and change the subject of the formula without thinking. But I'm not. I first of all substitute, and then I change the subject of the formula. If I need to do it that way, you need to do it that way as well. The reason I'm telling you to do that is that you gain more marks. If you've made a mistake with changing the subject of the formula, you will not get any marks. If you substitute into the wrong formula, you will not get any marks. Okay, so let's now do the maths or the arithmetic, and we're going to say V, multiply both sides by V, divide by 1,76, and we'll get V is equal to 3 times 10 to the 8, divided by 1,76. Now, I'm not going to try and do that in my head, so I'm going to put it on the calculator. And notice here on the Casio calculator, writing an exponential form, I write times 10 to the, and I can put the power in, 8. Very nice there. The other thing that I can then do is push the divide, 1,76, and I get an answer. Now, that answer gives me 170454545, comma 5. I don't want it like that. I want it in scientific notation. So what I'm going to do, because I know my scientific notation, I'm going to divide this by 10 to the 8, because I think it's still 10 to the 8. So I'm going to say divide by 1, exponent, 8, and see what it gives me. And it's going to give me exactly what I thought. The answer is 1,70. Notice the third place is a 4. So I'm going to leave it as 1,70. 1,70 times 10 to the 8. Okay. Don't forget about the times 10 to the 8. I was just showing that to you on the calculator because it gave it to me as a number, and we sometimes freak out, and it's not a scientific notation. You can change from normal notation, long decimal, to scientific, but I've shown you the long way around. I've shown you the mechanical way of doing it without taking the shortcut. But we're not finished. We need to put in units, always, meters per second. Now, guys, is this a realistic answer? Yes, it is. If it gave me a number bigger than 3 times 10 to the 8 meters per second, I know I've made a mistake. In this case, I know I'm all right. Okay. Next question. We did question 1. We're now going on to question 2. We're stepping it up. Guys, we need to step it up. You are almost grade 12s. Almost. Hey, the grade 12s don't listen to this, but they've only got a few weeks, and then they're going to be writing June exams, and then they're going to be into prelims, and then you're going to be the leaders. So you must make sure that you've got this sorted. Let's get going. So here we go. Calculate the refractive index, okay, of a cubic zirconia. If an angle of incidence of 30 degrees causes an angle of refraction of 13,26 degrees when light moves from air into a cubic zirconia. Now, Abram, do you know what a cubic zirconia is?
Nope.
Hey, come, Abram, you must know these things. It's time to talk jewelry now. Have I got a diamond or is it a cubic zirconia? You know, you could get fooled. That girl could be wanting the diamond.
Okay.
And you could just get the cubic zirconia. And then she's not going to be very happy with you.
No, she's not.
No. So, guys, we need to know the difference between our diamonds and our cubic zirconia. A cubic zirconia is just a stone that looks like a diamond, but it's not. Okay?
Okay.
And that's the important thing. You can get rings with cubic zirconia. But guys, here's a secret. The cubic zirconia cost about 1/10 of what the diamonds cost. So don't be a cheapskate like Abram. Don't go and buy your friend a ring and say, this is a diamond.
I wouldn't do that.
No, don't do that. Okay. So here we go. We're talking about, let's draw a picture. So what we're going to do is we've got air over here, and we've got our cubic zirconia over there. And I'm going to say, I want to have a normal. So there's my normal. And I want to show that at this point, it says the angle of incidence is 30 degrees. So at that point, I'm going to roughly draw it like that. Remember where the angle of incidence is. It's that one, measured from the normal. That's 30 degrees. Now, that's in air, and we know that the beam of light is traveling in, and now we're told it has the angle of refraction that is 13,26. So let me put that in. Notice it's got smaller. That means it's going from optically less dense to optically more dense, which kind of makes sense. So this angle of refraction over here is only going to be a small amount. It's only going to be 13,26 degrees. And that's theta r. This one is theta I. So what are we asked to do? We're asked to calculate the refractive index of the cubic zirconia. So we want to find N2. This is medium 1. This is medium 2. We know what N1 is. N1 is 1, 0, because air is just like the speed of light. In the air, the speed of light is close to c. We know it's 1. Okay, we've got that. Refractive index of air. If you're not sure, you need to learn that. Remember it. Now, what about the cubic zirconia? We don't know what it is. We're trying to find it. So what equation links for me the refractive index to angles, and need to find a missing one? I've got 3 bits of information. There's one that I'm missing. You've got it. It's Snell's law. So I'm going to write it down in the form that I wanted, in 1 times sine. Don't get confused. It's not cos or tan. It's just simply always sine. And we're talking about the angle of incidence. 1 and the angle of incidence go together. Then we go in 2 times sine theta of the refractive of the angle of refraction. Now, guys, substitute. Substitute everything that you know. And when you substitute, you're going to put it in brackets. What was 1? 1 was air. So we're going to put 1, 0. We're then going to put in brackets sine. What was the angle? 30 degrees. Make sure you put the degree sign in. What is N2? No, that's what we're trying to find. Don't be fancy. Substitute and even put this in brackets if you like. Sine of 13,26. 13,26 degrees. Close my brackets. Now I'm home away. Now it's not difficult. Because what I recognize is if I want to get N2 by itself, what I'm going to do is I'm going to take 1, 0 times the sine of 30, and I'm going to divide it by this amount here. I'm going to take this amount, and I'm basically going to divide both sides by that amount, which is the sine of 13,26. So let's set it up on the calculator, and hopefully we can find another function. And I'm going to try this one because I think it's a really nice little feature on the Casio calculator, and that's the fraction button. You don't always have to use it, but let's just show it to you here. So you push the fraction button, the little insert over there. I'll undo it again. It's just below the ABS sign, and we're going to open brackets, and we're going to say 1, 0, close my bracket, and then I'm going to multiply by, here we go, sine, and my angle was 30, close my bracket, and then to navigate to the denominator, I use the arrow button on the bottom. And I'm going to say, I want the sine of 13,26. So the bottom sine 13,26. Now, guys, I know some of you are saying to me, but I like to work out the denominator and numerator separately. That's fine if you want. But you can check it here. You've written it exactly as you put it on. There's no chance to make a mistake. Whereas if you work out each separately, what can happen in writing down the answer from one to the other, you might make a silly mistake. So I prefer to do it like that. And just to show the answer, I get the answer at being 2,1798. So I'm going to round off to 2 decimal places. It's a very good idea to always check in the front of your exam instructions how many decimal places if they don't tell you. Most cases, it will be 2 decimal places. So 2,179, I'm going to round that off to 2,178. So let me write that. 2,18, not 78, 1,8, 2,18. And that's the refractive index that I've got. Now, let's just check that this is the right refractive index, and hopefully it is. There we go. 2,8, 2,18 cubic zirconia. So at least we know, Abram, that these are pure cubic zirconia. We know that it is a cubic zirconia because we've applied Snell's law. And guys, that was a little hint for the challenge question. So I hope you've got my hint. I hope you're ready for the next question. So let's move on. It tells me the refractive index of something strange, gallium phosphide. I mean, who's ever heard of it? Who knows what it's used for? Well, maybe you can tell us. Google it and let us know. Post it on the page. They tell us that gallium phosphide has a refractive index of 3,15. If a ray of light moves from air through the gallium phosphide with an angle of incidence of 40 degrees, calculate the angle of refraction. Now, guys, I hope you can see it's again just Snell's law. So I'm going to do this one a little quicker, and I'm going to say we know N1, we know sine of the incident. We know that Snell's law says it's N1 times sine of the angle of incidence times N2 times the sine of the angle of refraction. Now, let's see what we know. We know N1 was moving from air, and N1 for air is 1, 0. We know that the angle was given as 40 degrees, so we know that. And we're wanting to find the angle of refraction. We know the N2, the refractive index of gallium phosphide, 3,15. So let's just substitute. 1, 0 times sine, just don't get it mixed up, read it, angle of incidence, yes, that's fine, 40 degrees, because they can be tricky. N2, 3,5, times sine of the angle of refraction. So how are we going to get the angle of refraction or on its own? Well, first of all, we'll divide through by 3,5. So I'm going to write here sine of theta r is equal to 1, 0 times sine of 40 degrees over 3,5. So let's go that far, because this is sometimes where you also make a mistake. Let's not make a mistake. I'm going to use the fraction button again. I'm putting in the 1, even though you don't have to. 1, 0 times the sine of 40, sine 40, and closing that, go down, and I'm going to say 3,5 on that side equals. Now, notice what it says. It gives me a ratio. It gives me a fraction, 0,18365. Now, yes, I know I can write that down, and I'm going to write it down now, but that's not my answer. That's the sign, 0,1836, whatever it was. Okay? That's what was given on the calculator. But I'm going to not want the sine of the angle theta. I want the angle theta. So how are we going to find that? So let's do this, because it's something that often catches you. And the way that I want you to make sure that it never catches you is I've been very deliberate. Whenever I've used an angle, I always put in the degree sign. And you can see here there's no degree sign. So I now know that what I've got to do is I've got to take the shift sign and I'm going to put answer. And I find that a very good trick to use. I'm going to take the second function, or the inverse of the sign, the back angle, in other words, the way to find the angle of the answer, which was that number, and I'm going to get the angle now, which equals to 10,58. 10,58 degrees. So we can say, therefore, the angle of refraction is 10,58 degrees. Whenever you've got an angle, please put in the degrees. Let's check. I did round it off correct to 2 decimal places. 10,58. The next one was a 2, so the value is fine. I think there's time for one more. Let's pick it up and let's see if we can get through it. So it now tells us that we've got a second scenario. We've got 1,5 oil, a layer of oil, and we've got water, 1,33. The angle of refraction of a ray moving from the oil to the water is 35 degrees. So remember, it's moving from the oil to the water. We're asked to calculate the angle of incidence with which the light hits the oil. So let's make sure it's from the oil into water. oil over here, water over here, and I'm going to, again, put in the normal, draw the diagram, and let's see what we've got. We've got told that the angle of refraction is 35. So it's going from oil into water. Now, before we get there, so we can draw our diagram properly, let's just remember that N in water is 1,33, and the one in oil is 1,55. So the N over here is 1,45. Not 55, 45. Got it right. So guys, please notice it's moving from an optically more dense object, a substance, material, to a less dense. That means that we shouldn't be surprised that the angle of refraction is big. So I'm going to draw it, and it's told me what the angle of refraction is, 35 degrees. I'm going to draw it in here like that. And I'm going to say that this is the angle of refraction. It's 35 degrees. And that's theta r. I now need to just sketch in my own mind. I'm going to decide that the angle of incidence is going to be less than 35. It's going to be smaller than 35 because it bends away from the normal. It's slow. It's speeding up. Okay, very important that you can talk your way through this. It's going from a more dense material to a less dense material, therefore it's speeding up. It's like going from water into air. It will bend away. And so what we're trying to find very quickly is that angle. Okay, and now we've written it out like that. I don't think there's too much problem with it. All we've got to do, Snell's law, sine theta I is equal to N2 sine theta r. Now, substitute first, and here we mustn't make the confusion. Oil is 1,45, 1,45, multiplied by the angle sine theta I don't know that one. N2 was 1,33. I'm going to rush it, 1,33. And the sine here was the sine of 35 degrees. Don't forget the degree sign. So now that tells me that sine of theta I is equal to 1,33 times sine of 35 degrees divided by 1,45. So get out the calculator, and here I'm just going to do it the ordinary way. So I'm not going to use the fraction button. I'm going to say 1,33 times the sine of 35 divided by 1,45. And if you try it both ways, you'll see you'll get the same answer, 0,5261. 0,526, 0,5, sorry, I just want to check it. Was it 26? Yes, it was, 526, 5261, dot, dot, dot. I'm now going to take my, I want the inverse of that because that was sine theta. I'm going to say shift, sine, answer, equals. And here I get my angle, 31,74. So my angle of incidence, 31,74 degrees. Does it make sense? Well, yes. It's smaller than the 35. 31, what was it, 74? It's smaller. That's what we predicted. It would be smaller. 31,74 degrees makes sense that it should be because the refractive indices are quite close to each other.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to download the show notes and to watch all the videos from this year's shows. Goodbye.